Now we want to talk a little bit about spherical symmetry, and we're going to motivate another coordinate system, which is the spherical coordinate system, which is very useful in analyzing objects with spherical symmetry. Now, an example of spherical symmetry that appears all over the place in the universe is where density is a function of distance from the center. That's typical of planets and other large astronomical objects, stars. So it's typical of large astronomical, whatever astronomical means in this context, large astronomical objects which are not unduly influenced by the gravitational pull, let's just say external gravitational forces. And what I mean by that is simply that when you have something big enough, gravity becomes really prominent in the behavior of that object and tends to push everything into a sphere, tend to pull everything into a spherical shape. With the denser elements being pulled in closer to the center and being compressed to withstand the gravitational pull of the mass that lies outside of a given distance. And I don't want to go too much further into that description or that statement, but if you're in that course, you're likely to be along a track that will, and probably already has, taken you into enough physics to understand a lot of what I just said and what I haven't said. Another typical phenomenon would be hailstones, which tend to have ice densities in shells. Some of the ice is more porous than the ice at some of the points in the stones tends to be a little more porous than the ice at other points. So there is a more or less spherical symmetric, more or less symmetric spherical distribution of mass in hailstones. They rotate randomly as mass is accumulated during the up and down motion in a thunderstorm, the repeated up and down motion, and other phenomena for different reasons also tend to exhibit a spherical density function. So that if we represent the sphere, and of course we're just going to represent a cross-section of the sphere with center here, the one thing that influences its density, the density at a point, is simply the distance from the origin, and that distance is going to be the same around any concentric sphere. Wish me luck. It's not coming out too bad, but I'm probably going to choke. Okay. So here's a sphere, and here's a concentric sphere within the larger sphere. Think a planet and think a concentric sphere, a sphere with the same center. And on that concentric sphere, the density is going to be constant. Now this distance from the center I could call r. Of course, we'd probably use a big R for the radius of the sphere. And one problem with using small r is it could easily be confused with a polar or cylindrical coordinate. So I'm going to use the Greek letter rho. So let's let this be the radius or the distance rho from center. Then this concentric sphere would be characterized by rho equals constant. Whatever this distance is, it's constant over the sphere. And of course that sphere isn't just in this plane, it rounds out this way and so forth. It makes a ball within a ball. All the points at whatever this constant distance is from the center lie on that sphere. So what we want to do is we want to devise a coordinate system a spatial coordinate system based on rho. Now we need more than just distance from the center to specify a point. So the question is, how do we specify a point in a system where rho is one of the coordinates? Rho being, again, the distance from what we're going to regard as a central point and what is going to be identified with our origin. We also want to make our system, see if I've got room here, okay, make the system as compatible as possible with rectangular coordinate system and cylindrical coordinate system. So in the next clip we'll start talking about how to do that and then how to do our integrals and other calculus operations within that system.